Welcome to the first lecture, Challenges of Microwave Design. If you look at the universe, there are a lot of stars. Some of them are radio stars which emit radio frequency signals. Lot of microwave radiation they emit, and by properly listening to them, we can get many information from these radio sources. Microwave technology is required to listen to these type of extraterrestrial sources. You see sun emits solar flare which affects which falls on our atmosphere, which can disturb our communication. So, there also you need to understand microwave technology, that in such cases what to do, how to shield our communication systems, our various application systems insulated from those solar flares. You see, this is a very common thing. We see lightning. Now, we have various systems man has made which needs protection against this lightning. So, to understand that, you need to understand microwave technology. All of you know that now our Mother Earth is surrounded by so many satellites. Now, these are, most of them are artificial satellites which man has launched so that to extend our vision into space. Now, to communicate with them, to gather data from them, you need to understand the technology of microwave. You see, today's world, all of us are surrounded by Wi-Fi, satellites, mobile towers, you have TV, pagers, you have cell phones, you have various communication antennas installed on ground, you have your computer. Everyone radiates and receives electromagnetic signal. To understand that, you need to know the technology behind them, which is microwave technology. You see the electromagnetic spectrum, you see starting from very large wavelengths or of the order of a large soccer field, a large stadium, to very small wavelengths like a water molecule, a electron, a subatomic particle. All these are composed of electromagnetic waves. So, the electromagnetic spectrum covers from very small frequency to very high frequency, typically 100 hertz to you can go up to 10 to the power 20 hertz. So, all these are part of electromagnetic spectrum, but as you can see from this slide that there is a broad division of radio waves and microwaves, which roughly we can say from kilohertz sort of frequencies to gigahertz sort of frequencies we roughly call radio waves, and a part of that, particularly you can say 100 gigahertz to roughly 100 gigahertz, 100 megahertz to 100 gigahertz, that is called microwaves. So, basically in this frequency range we have certain techniques to handle all these applications, etc. Now, you see there are some inventions which happened in the 20th century. There were radios, radio communication was invented just at the start of the 20th century. by transatlantic communication. Then we have seen TV communication, etc. Now, due to invention of radio, this radio communication, TV communication, this became possible. You know, also at the same time, in the dawn of the 20th century, there was aircraft was invented, which gave rise to the field of avionics, aircraft electronics, which also gave rise to a microwave eye to mankind, that is called radar, by which you can detect aircrafts or any other thing that is coming to you. Also, you know, in the middle of the century, last century, there was invention of transistor, and that gave rise to IC, integrated circuits, in a very small volume or area, large number of those transistors and other circuitries, electronic circuitries are packed, and now we are seeing the very large scale integration. So, there also this microwave technology is useful, because when two transmission lines are very nearby, there is lot of coupling issues, etc., crosstalk, and all those are analyzed by this technology of microwave. Then you know that in the 70s or 80s of the last century, there were invention of microprocessor, and that gave rise to digital control of everything, and finally microprocessor evolved to computers, which have proliferated today's our households. And in all them also, when today we are having the clock speed going to almost gigahertz, so there are lot of electromagnetic waves that come out from them, and you require microwave technology to understand them. Like for example, we see an application here. Suppose all the countries are nowadays sending the planetary explorating various satellites, various rovers, various orbiters. So, now if you want to find out what is there in a new planet, you see that you flow the satellite, like the slide is doing, that it is focusing on various parts of the planet, and then it is gathering the reflected data, and from that you see that there is a slice, that one layered information you can take out. You go on doing that for various layer after layer under the soil of the planet, and you get various layers of information by which scientists can predict, space scientists predict what are the various layers composed of, whether there are various minerals, whether there are various valuable minerals which are not available in earth or which are scarce in earth, they also can be extracted and taken. Similarly, you see that suppose you have a new area, and there you want to start your various communication, your radars, etc., you want to deploy. So, you want to first understand what is the ambient that is present there. For that, you need to find out how the electric field look like. In this slide, you can see that how the electric field is looking place in a particular terrain. So, to do this, you require those tools of microwaves, which we will discuss in this lecture. Then this was a fairly recent development, that nowadays we want to send very short pulses of the duration of, let us say, 150 picosecond. Now, when a nuclear explosion takes place, this type of pulse come to earth. So, we need to know that what happens if our systems get exposed to that. But generally, mankind did not have any means by which we can either detect or we can radiate this type of signals, but in 1995 this antenna called impulse radiating antenna was developed purely from this microwave technology standpoint. So, that now you can create a field of 5 kilovolt per meter at 300 meters, that means quite 300 meters away. If you can create a kilovolt per meter order of the field with a pulse duration of 150 picosecond, so that you can produce by one pulse a huge band of frequencies 40 megahertz to 4 gigahertz. Now, this is purely when the microwave technology was applied, this antenna came out. It was not known throughout almost the last century, but fortunately in the last decade of the century 1995 we got this antenna, which has got tremendous application today, and it has changed the whole ball game of microwave technology. This is a better view of that antenna. You can see it is a dish antenna, but there are on the back of it there are transmission lines properly designed, so that a pure pulse, almost an impulse sort of thing, you can radiate through them. Now, application, you see, when a person, suppose there is an earthquake or an avalanche, and then a person is buried under that earthquake debris or due to the snow of the avalanche. Now, we want to first detect whether there is any person there. Now, there were no probes before, tracker dogs etc., or helicopter could not see whether what is there in the subsurface, but with that technology, that impulse radiating antenna, now people can find out whether there is any person or any object which is hidden behind say 1 to 2 meters of snow or 1 to 2 meters of those debris, and then you can also, technology is coming up by which you can detect whether he is dead or alive, so that whether rescue operations are needed. Now, so we see that there are a lot of applications where this RF design or microwave design we say is needed. Now, generally in our undergraduate classes, at the initial stages we are taught various analog and design procedures, like you are taught the how to design an C amplifier, how to design a FET amplifier, how to design a filter etc. But RF design is a bit different from that, because it evolves from primarily from electromagnetic field theory, then as a technology it evolves from microwave technology. Now, what are the salient points where this RF design differs from microwave design? RF design differs from the baseband analog or digital design. So, the first thing is, you see, impedance matching. Actually, you know from maximum power transfer theorem that if there is a source or a source of energy, source of power, electronic power, AC power, that you want to deliver to a load, then load and source should be matched. There should be a conjugate relationship between them, so that maximum power can be transferred. But unfortunately, fortunately in analog or digital baseband design, this is not always applied, because there are in baseband, that means where your basic source, either it is a audio source or a video source, those things which are at lower frequencies, typically some kilohertz or megahertz frequencies, small amount of megahertz frequencies are there, then you have plenty of those source and their energy. So, power is not a problem, that is why they try to maximize those voltage etc. from those designs. But when we go higher up in frequency, then producing power is very costly. So, it is a costly resource, that is why the RF design people, they take very special care about how to maximize that transfer of power from one network to another network. That is why they are very they take lot of care for this impedance matching, whereas we can say that the analog or digital design are indifferent to that. One example I will say, that when we design a C amplifier, we try to say that our design goal is we will have maximize the input impedance and minimize the output impedance. But from the maximum power transfer theorem, we are not at liberty, because what is the source, we will have to match to that both in the input side and the output side, but we can take that liberty in the case of the low frequency design or baseband design we call, and our typical analog digital designs that we see there, because they have plenty of power. So, even if it is not optimum in the power sense, the design of a C amplifier, which is a classic very good amplifier, voltage amplifier sort of thing, there we do not pay heed to the maximum power transfer theorem, whereas in an RF frequency or microwave frequency you are bound to pay this attention. That is why impedance matching is an important concept for RF design, and we will have special lectures for tackling how to do those impedance matching. Then you see that generally in lower frequency thing we are taught about I diagram, that if you have a digital signal, then generally how much the interference is causing you disturbance we see through I diagram. But in the microwave region, generally the more important frequency response of an any block, an amplifier block or oscillator block or mixer block, etc., we always see, because we know that if you change frequency and when you are at higher frequency n, then the basic building blocks at different frequency they behave differently. Like a capacitor, at certain frequency it can be behaving as a capacitor, but if you change the frequency it may also become a resistor or an inductor. The same thing for an inductor becoming capacitor at some other frequency. So, frequency response is an important thing, and always you should be aware that if you change the frequency, a whole new circuit from the same components you can get. So, that is why frequency response is a very useful thing for RF design. Then generally it is seen that digital circuits, etc., they talk of time domain, whereas it is apparent that more concentration is given in RF design for frequency domain. One of the reason also is that, as you have seen, that those very short pulse type of signals like impulse signals, etc., previously RF circuits were not able to pass that, but nowadays this distinction is coming down. Also in time domain there are a lot of microwave technology coming up, but whatever is existing in which frequency domain is a useful thing for RF design. Then you see to see any device, like since you know that in low frequency thing we look at oscilloscopes to look at an waveform, but at higher frequency we need to see by changing frequencies how the behavior is taking place, and also we need to have a wave sort of picture, that means whether there is a wave going in forward direction or getting reflected and coming into backward direction. So, that is not available from oscilloscope. That is why the basic instrument that is used at RF frequency is network analyzer. That is why we will see network analyzer also at the end of this series of lectures or this course. Then the basic unit in which the analog or digital baseband designs, they generally talk of voltage. If that voltage range is the range is quite high, then instead of an absolute scale, it is generally expressed in dB scale. So, dB volt is the one that they talk of, but in RF designs we talk of power, not only voltage, but the cross product of that voltage and current that gives us the power. So, the unit of power in the dB scale is dB watt. So, we talk of dB watt. I think all of you know that if there is an absolute scale of, suppose I have 10 watts of power, 10 watts of power, then equivalently this I can also convert to dBW watt of power, dBW of power. How? Since it is a power quantity, I will have to take 10 log to the base 10 this quantity 10. So, this multiplier is for power quantities, it is 10 log 10 10 dBW. So, by this you can calculate any of the power to dBW watt. Also there is another watt which will another unit of power which we will be using in this thing, that is called dBm power. Powers another unit is dBm, because generally in RF frequency, in particularly in our applications or in laboratories we deal with smaller amount of power. So, dBm means that you convert this watt to milliwatt. So, the same 10 watt of power will be in milliwatt. If I put, it will be how much, that it will be multiplied by 1000. So, 10,000 milliwatt. So, if I to get dBm of power, the same power will have to be written as, since it is power, again the multiplier is 10, but log 10 then 10,000. So, that will be that it will be 4. So, I will have 40 dBm of power, whereas here I had that 10 dB watt of power. So, this is the power units that in RF frequency we generally use. Now, another thing is, you see, generally since the same reason that we are scarce of power. So, RF at RF people, the instruments etc., that is designed generally for 50 ohm of power, 50 ohm impedance. So, it is a small impedance, whereas oscilloscope probes, they are kilo ohm or mega ohm sort of impedance. You have seen that in your oscilloscopes, the probes that are coming, you can change it to 1 ohm or 10 ohm probes etc. So, you see the reason of this difference is, if you consider power is given by, as the slide shows, that power is given by V square by Z. So, for a same voltage, if you give smaller Z, smaller impedance, you get more power. That is why the RF people uses 50 ohm, whereas oscilloscope people, they are interested in baseband, people are interested about the voltage. So, voltage is given by root over Pz. So, more impedance means you will get more voltage when the same power is given. That is why the non-RF people, they love higher impedance, RF people loves lower impedance. Then also typically the RF has higher current drain, typically of the order of milliampere, whereas in a typical digital block, particularly with semiconductor technology, you have of the order of microampere or even smaller. So, current wise RF people, they have more power compared to that, again due to the same reason that the impedance is small for RF people. That is why the current, for the same power, the current will be higher in case of RF designers. Then you see that where the RF things are placed, this shows typically the left side is showing the, you see this left side diagram is a satellite system. So, you see that there is an electromagnetic wave coming from the satellite falling on the receiving antenna, then there is some amplifier etc., then there is some band pass filter, mixer, again a band pass filter, fast IF amplifier. So, all these is part of your RF. That means, these are all at typically gigahertz or several 200, 300 megahertz sort of thing. So, that is why we call it RF front end. Generally before or after the antenna, the systems, those are called RF front end. So, there you need to apply these principles that we will be learning in this course, some of the principles. So, that you will have to apply into your design. Whereas, if you see the right side things, that typically in a non-RF system like your from this antenna, finally this after this IF amplifier, it comes to finally a demodulator sort of thing. So, after demodulator you have, there is a forward error correcting decoder, then there is a baseband processor, then onboard controller, forward error correcting controller, modulator. So, all these you have learnt in your other courses. So, these are basically typically a baseband processing blocks like demodulators, error control coding, error decoding, baseband processing, then your various modulation things. Those are generally the non-RF things or analog or baseband things. So, they are a bit away from the antenna. So, placement wise also there is a clear cut demarcation in any system. If you look in any radar system, in any communication system, the RFs, they are at the forefront when they are pumping the power to the free space or outside world, and the back end, that is generally the RF, non-RF things. Now, that is why, as I am saying, that the this RF people, they are power conscious, whereas status means the voltage, because most of the decisions in the baseband things, they are taken by whether a certain thing is above a particular voltage threshold or below 5 volt, or it is more than 5 volt or less than 5 volt, more than 2.5 volt TTL logic or not. So, there it is a status conscious thing, whether in RF it is how much power and etc. And generally modulators are the confluence of this baseband and the RF blocks. So, this similarly in a receiver, demodulator is the confluence of these two blocks, and generally baseband we call status conscious, RF power conscious, and also they have different tasks. By now I can summarize that power transportation is the basic task for RF, whereas voltage transformation is the basic task for our baseband systems. Now, what are the challenges of RF design briefly? That we need to consider various parameters. You see, one of the parameter is power gain, not voltage gain. The next is how much noise, because since you are opening up to the outside world, you are also giving or taking lot of outside noises. Suppose a lightning takes place, suppose some star is radiating, radio star, all those your antenna is picking up. So, you are getting noise. So, you need to find out what is the noise power you are getting. That is why we talk of signal to noise ratios, etc. Then whether you are maintaining linearity in your devices, because if you do not maintain linearity, a particular frequency in which you are working, you will generate some other frequencies due to that non-linearity, which will create trouble for you, because we have seen that if you change the frequency, the whole ball game is changed in an RF circuit. So, these are the three very important parameters in RF design, but there are also, when you if you design an active circuit like an amplifier etc., you need to consider stability of that. You need to consider that to operate this RF signal, how much DC power supply you have used. You need to find out also what is the current drain. You need to find out what is the part count of that. Then there are some special parameters which are not always applicable in RF, but in some critical blocks they are very important. Like if you have a voltage control oscillator, they are due to the change of load, the frequency of the oscillator changes. So, load pooling in VCO is an very important parameter for oscillators. Similarly, in the VCO or oscillators, there is a phase noise created, that is also a very important parameter, because if you do not characterize that properly, lot of functional disability come for other parts of the network. Then how much is the power added efficiency for a power amplifier? Power amplifier is before the transmitter is radiating, there is a power amplifier, its efficiency is very important in communication. Then sensitivity of a receiver. So, how small a signal you can sense when you are sensing a radio star sending from millions of kilometer away his signals, you need a receiver, very sensitive receiver for detect that. So, for RF receivers, they need to characterize what is the sensitivity of the receiver, and obviously when you are pumping power, you are trying to communicate, you are trying to send the signal. Another characteristic for a transmitter or parameter for a transmitter is how much output power you are trying to generate. So, with this we come to the basic what are the challenges. So, definitely I think you have understood that there are a lot of challenges in RF design. So, we will see some tools in our next lectures by which we can address this type of challenges. Thank you.